Drop a cup on the floor, it breaks. Pieces scatter everywhere, sharp fragments, dull thuds, the sound of something irreversibly destroyed. Now sit there and wait. Wait for the pieces to jump back up. Wait for them to fly through the air and reassemble themselves perfectly in your hand. You can wait as long as you want. It's not going to happen. You know it's not going to happen. Everyone knows it. It's obvious. But why? Let me show you. It's obvious to everybody that the phenomena of the world are evidently irreversible. By that I mean things happen that don't happen the other way. You drop a cup and it breaks, and you can sit there a long time waiting for the pieces to come together and come back into your hand. If you watch the waves breaking at the sea, you stand there and wait for the great moment when the foam collects together, rises up out of the sea, and falls back further out from the shore. It would be very pretty. As a matter of fact, the demonstration of this in lectures is usually made by having a section of moving picture in which you take a number of phenomena and run the thing backwards, and then see all the laughter. The laughter just means this ain't going to happen in the real world. But actually, that's a kind of weak way to put something which is so obvious and deep as the difference between the past and the future. Because even without an experiment, our very experiences inside are completely different for past and future. We remember the past. We don't remember the future. We have a different kind of awareness about what might happen than we have of what most likely has happened. The past and future look completely different psychologically. The questions of memory, of apparent freedom of will, in the sense that we feel we can do something to affect the future, but none of us, or very few of us, believe that there's anything you can do to affect the past. Remorse and regret and hope are all words which distinguish perfectly obviously the past and the future. Now, if the world of nature is made of atoms, and we too are made of atoms that obey physical laws, this obvious distinction between what happens in the past and the future, this obvious irreversibility of all phenomena, you would think the most likely and obvious interpretation is this: that some laws, some of the motion laws of the atoms, are going one way, that the atom laws are not such that they can go either way, that there's somewhere in the works some kind of principle that makes things only work one way and never the other way. And so the world is turning from an ordered character to a disordered character all the time. And this one-way business of the interactions of things is the thing that makes the whole phenomena of the world seem to go one way. Yet we haven't found it yet. That is, in all the laws of physics that we've found so far, there doesn't seem to be any distinction between the past and the future. The moving picture should work the same way, going both ways. And the physicist who looks at it should not laugh. Let me show you the details. Let us take the law of gravitation as our standard example. If I have a sun and a planet that I started off in some direction going around, and I take a moving picture of this, say it gets to here. Now take a moving picture and run the movie backwards. What happens? The planet goes around the sun in an ellipse. The speed is such that the area swept out by the radius is always the same in equal time. It just does exactly the way it ought to do. Perfectly satisfactory. It cannot be distinguished from the one going the other way. So the law of gravitation is of such a kind that it doesn't make any difference if you show any phenomenon involving just gravitation running backwards on a film. It'll look perfectly satisfactory. Put it more precisely this way. If at a given instant all the particles in a complicated situation would have every one of their speeds reversed suddenly, then the thing will just unwind through all the things that it wound up into. That is, if you have a lot of particles doing complicated things, then you suddenly reverse all the speeds. They will completely undo what they did before. This is in the laws of gravitation. If I reverse the time, the forces are not changed, and so the changes in velocity are not altered at corresponding distances. Each velocity, then, has its succession of alterations made in exactly the reverse way that they were made before. It's easy to prove that the law of gravitation is time reversible. The law of electricity and magnetism, time reversible. The laws of nuclear interaction, time reversible as far as we can tell. The laws of beta decay, also time reversible. There were some experiments a few months ago which indicate that there's something unknown about certain laws. Suggests the possibility that maybe it's not time reversible, but we shall see. But at least the following is true. This beta decay, which may not be time reversible, is a very unimportant phenomenon for most ordinary circumstances. The possibility of my talking to you does not depend on that happening. It depends on chemical interactions, electrical forces, gravitation. But I am one-sided. I speak, and the voice goes out into the air and doesn't come sucking back into my mouth when I open it. This irreversibility cannot be hung on the phenomena of beta decay. In other words, we believe that most of the ordinary phenomena which are produced by atomic motions follow laws which can be completely reversed. So we have to look elsewhere to find the explanation. If we look more carefully at planets moving around the sun, you'll soon find that it isn't quite right. For example, the Earth's rotation on its axis is slightly slowing down. That's due to tidal friction. You see that friction is something which is obviously irreversible. If I took a heavy weight on the floor here and pushed it, it would slide and stop. If I stand and wait for it, it doesn't suddenly start up and speed up and come into my hand. So a frictional effect seems to be irreversible. But a frictional effect is the result of enormous complexity of the interactions of the block with the wood, the jiggling of the atoms inside. The organized motion of the block is changed into disorganized, irregular wiggle-waggles of the atoms in the wood. So we should look at the thing more closely. As a matter of fact, we have here the clue to the apparent irreversibility. I'll take a simple example. If we have blue water, say ink, and white water, that's water without ink, in a tank with a little separation, and pull out the separation very delicately, then it starts out separate, blue on one side, white on the other side. Wait a while. Gradually, the blue mixes up with the white. And after a while, the water is Luke blue. I mean, it's sort of 50-50 color, uniformly distributed throughout. Now, if we wait for a long time and watch this, it does not by itself separate. Oh, you can do something. You can evaporate the water and condense it somewhere else, and collect the blue dye, and dissolve it in half the water, and put it back. But while you're doing all that, you yourself are causing irreversible phenomena somewhere else. So by itself, it doesn't go the other way. And that gives us some clue. Let's look at the molecules. Suppose we took a moving picture of the blue and white water mixing. It would look funny if we ran it backwards, because we'd start with uniform water, and gradually the thing would separate, and that would be obviously nutty. Now we magnify the picture so that every physicist can watch, atom by atom, to find out what happened irreversibly, where the laws of balance, of forward and backward, broke down. You start and you look at the picture. You have atoms of one kind and atoms of another kind jiggling all the time, in thermal motion, wiggling and bouncing. If we start at the beginning, we have mostly atoms of one kind on one side and atoms of the other kind on the other side. Now these atoms are jiggling around. You need billions and billions of these atoms. These atoms are jiggling around, and if we start all on one side and all on the other, we see, of course, that in their perpetual irregular motions, they'll get mixed up. And that's why it gets to be more or less uniformly blue. But let's watch any one collision. Here's a particular collision selected from that picture. Here's this molecule moving this way, and this one moving this way. They come together in the moving picture, and they bounce off in different directions. Now you run that section of the film backwards. You find a pair of molecules moving toward each other, bouncing off in different directions. And the physicist looks with his keen eye and measures everything and says, that's all right. That's according to the laws of physics. If two molecules came this way, they would bounce that way. And if they came that way, they would bounce this way. It's reversible. The laws of molecular collision are reversible. If you watch too carefully, you can't understand it at all, because every one of the collisions is absolutely reversible, and yet the whole moving picture shows something absurd. In the reverse picture, the molecules start in this condition: blue, white, and blue, white, and so on, all mixed up. And yet as time goes on, through all the collisions, the blue separates from the white. They can't do that. That's not natural, that the accidents of life will be such that the blues will separate themselves from the whites. Yet if you watch the reverse movie very carefully, every collision is okay. Well, you see, that's all there is to it. The irreversibility is caused by the general accidents of life. If you start with a thing that's separated like this and just make irregular changes, it gets more uniform. But if you start with something that's uniform and make irregular changes, it doesn't get separated. It could get separated. It's not against the laws of physics that these things bounce around so that they separate. It's just unlikely. It just would never happen in a million years. And that's the answer. The things are irreversible only in the sense that going one way is likely, but going the other way, although it's possible and is according to the laws of physics, wouldn't happen in a million years. It's just ridiculous to expect that if you sit there long enough, the jiggling of the atoms will separate a uniform mixture of ink and water into ink on one side and water on the other. Now if I had put a box around here so that this was all the molecules that there were, as time goes on, they would get mixed up. But if you're patient, I think you could believe that in the perpetual irregular collisions of these molecules, after some time, not necessarily a million years, maybe only a year, if you keep watching, accidentally they get back more or less like they started. It's not impossible. However, the actual objects with which we work have not only 4 or 5 atoms, they have 4 or 5 million atoms. And it's just not likely that 4 or 5 million atoms are all going to get separated like this. So the apparent irreversibility of nature does not come from the irreversibility of the fundamental physical laws. It comes from the characteristic that if we start with an ordered system and have the irregularities of nature bouncing, then the thing goes one way. Therefore, the next question is, how did it get ordered in the first place? That is to say, why is it possible to start with order? Because you see, the difficulty is that we start with an ordered thing and we don't end with an ordered thing. One of the rules of the world is that things go from an ordered condition to a disordered one. Incidentally, this word order and disorder is another one of those terms of physics which aren't exactly the same as in ordinary life. The order need not be interesting to you as a human. It's just a question of whether there's a definite situation, all on one side and all on the other, or they're mixed up. That's order to disorder. Maybe you like it better mixed up, but that's not more ordered. Now the question is, how does the thing in the first place get ordered? And why, when we look at any ordinary situation which is only partly ordered, can we conclude that it probably came from something more ordered? If I look at a tank of water in which it's very dark blue on this side and very clear white water here and sort of bluish water in between, and I know that thing has been left alone for 20 or 30 minutes, then I will guess that it got this way because it was bluer before. The separation was more complete in the past. If I wait longer, the blue and white would get more intermixed. If I know this thing has been left alone for sufficiently long, I can conclude something about the past condition. The fact that it's smooth here could only arise because it was much better in the past, much more satisfactorily separated. Because if it weren't more satisfactorily separated in the past, in the time since then, it would have gotten more mixed up than it is. It is therefore possible to tell from the present something about the past. Although physicists really don't do this much. Physicists usually like to think that all you have to do is say, these are the conditions, and what happens next. But all our sister sciences have a completely different problem. In fact, all the other things that are studied, history, geology, astronomical history, all have a problem of this kind. They are able to make predictions of a completely different type than a physicist. A physicist says, in this condition, I'll tell you what will happen next. But a geologist will say something like this: I have dug in the ground, and I've found certain kinds of bones. I predict that if you dig in the ground, you'll find a similar kind of bone. A historian, although he talks about the past, can do it by talking about the future. When he says Napoleon existed, or the French Revolution was in 1789, he means that if you look in another book about the French Revolution, you'll find that same date, 1789. The thing that he says makes a kind of prediction about something he has never looked at before. Documents that have still to be found. He predicts that the documents, if there's something written about Napoleon, will coincide with what is written in other documents. The question is, how is that possible? The only way that's possible is to suggest that the past of the world was more organized in this sense than the present. Some people have proposed, some physicists have proposed, that the way it got ordered was this: that the whole universe is just irregular motions. And if you wait long enough with 5 atoms, of course it can get separated accidentally. All that has happened is that the world has been going on and going on and going on, and it fluctuated. That's what this is called, when it gets a little bit out of ordinary. It fluctuated, and now we're watching the fluctuation undo itself again. How do we know that isn't the case? You say, well, how long would you have to wait? I don't know. But if it didn't fluctuate far enough to be able to produce evolution, to be able to produce an intelligent person, we wouldn't have noticed it. So we had to keep waiting until we were alive to notice it. So we have to have at least that big a fluctuation. But this is incorrect, I believe. I think that's a ridiculous theory for the following reason. If the world were much bigger, and there were atoms all over the place, and they started from a completely mixed up condition all over, and I happen only to look at the atoms here, and I find that the atoms here are separated, I have no way to conclude that the atoms anywhere else are separated. In fact, if the thing were a fluctuation and I noticed something odd, the most likely way that it got there is if there's nothing odd anywhere else. I have to borrow odds, so to speak, to get this lopsided. And there's no use borrowing too much. It's much more likely, of all the possible ways in which these atoms can be on one side and these on the other, that the most likely condition of the rest of the world is mixed up. Therefore, an astronomer looking at a star he's never seen, although when we look at the stars and we look at the world, we see it's ordered. There could be a fluctuation, but the prediction would be that if we look at a place we haven't looked at before, it'll be disordered, a mess. The separation of matter into stars which are hot and space which is cold. If you say it could be a fluctuation, then in places we haven't looked, we would expect that the stars are not separated from the space. But every time we make a prediction that in a place we haven't looked, we'll see the same statement about Napoleon. We'll see stars in a similar condition. We'll see bones like the bones we've seen before. The success of all those sciences indicates that the world did not come from a fluctuation, but came from a condition which was more separated, more organized in the past than at the present time. Therefore, I think it's necessary to add to the physical laws the hypothesis that in the past the universe was more ordered, in a technical sense, less mixed up than it is today. This statement is the added statement that's needed to make sense and to make an understanding of the irreversibility. That statement, of course, is itself lopsided in time. It says something about the past is different than the future. But it comes outside the province of what we ordinarily call physical laws. Because we try today to distinguish between the laws which tell how something moves if you start it in a certain way, and those statements about how the universe got the way it is, or what it was in the past, the statement of the physical laws which govern the rules by which the universe develops, and the statement of the condition the world was in the past, that's considered to be astronomical history. Perhaps someday that will also be part of physical law. Now there's an interesting feature of irreversibility I'd like to illustrate. One is to see how exactly an irreversible machine really works. Suppose we built something we know ought to work only one way. What I'm going to build is a wheel with a ratchet on it. A ratchet is a notched wheel with teeth, like a sawtooth. And there's a little piece called the pawl, held down by a spring, that gets in the way of the wheel. Now this wheel can only turn one way. If you try to turn it backward, the teeth jam against the pawl and it doesn't go. But if you turn it forward, it just clicks right over. They use them in clocks, so when you wind watches, you can only wind them one way. You see, it's completely irreversible. The wheel can only turn one direction. Now here's the clever idea. Because of molecular motion, perpetual jiggling, molecules are always bumping into things irregularly. If you build a very delicate instrument, it will always jiggle because it's being bombarded by air molecules. So we connect vanes to this ratchet wheel and put them in a box of gas. The molecules bombard the vanes irregularly, pushing them sometimes one way, sometimes the other. When it's pushed backward, the ratchet jams. But when it's pushed forward, it clicks around. So the wheel should perpetually turn in one direction. Perpetual motion from molecular jiggling. But we have to look at the details. When the wheel turns, the pawl lifts up and snaps back down against the next tooth, and it bounces. The wheel could go backward when the pawl accidentally bounces up. This will not work unless when the pawl comes down, it sticks, and that requires friction, and friction generates heat. So this part of the wheel gets hotter and hotter. But now something interesting happens. Just as there's irregular motion in the gas making the vanes jiggle, the pawl itself starts getting hotter and starts jiggling from molecular motions inside it. So a time comes when the pawl is bouncing up and down so much from the heat that when it's up, a tooth can go either way. In fact, the thing will be driven backwards. If the pawl side is hot and the vane side is cold, the wheel goes the wrong way, because every time the pawl bounces down, it hits an inclined plane and pushes the wheel backward. So it turns out that no matter how you design it, a ratchet like this will go one way if this side is hotter, and the other way if that side is hotter. But after heat exchanges between the two, and everything calms down to the same temperature, it will go neither way. That's the technical demonstration that phenomena of nature only go one way as long as they're out of equilibrium. As long as one side has a different temperature than the other, or one side is more ordered than the other. The conservation of energy would let us think we have as much energy as we want. Nature never loses or gains energy. Yet the energy of the sea, for example, all that thermal motion of atoms, is practically unavailable to us. To make energy useful, to make it available, we need a difference in temperature. Without that difference, although the energy is there, we cannot use it. There's a great difference between energy and availability of energy. Let me give you an analogy. You go to the beach with towels. A sudden downpour comes. You grab the towels and run to the bathhouse. You start drying yourself. This towel is a little wet, but drier than you. You use it. Then you try another, but it's too wet. It's wetting you as much as drying you. Pretty soon you discover something horrible. All the towels are damp, and so are you. No matter how many towels you have, there's no way to get drier, because there's no difference between the wetness of the towels and the wetness of yourself. When everything reaches the same dampness, you're stuck. The thing that corresponds to dampness is temperature. When two things are at the same temperature, it's just as easy to pick energy off one as off the other. So if you put them together, they exchange energy back and forth, but the net result is nothing. When everything is at the same temperature, there's no more energy available to do anything. The principle of irreversibility is this: if things are at different temperatures and left to themselves, they become more and more the same temperature, and the availability of energy perpetually decreases. This is the entropy law. Entropy always increases. Or to say it another way, the availability of energy always decreases. Things of different temperature, left to themselves, tend to become the same temperature. But two things already at the same temperature don't spontaneously split apart, one getting hot, one getting cold. The one-wayness is always the loss of available energy. Here we have an example where an obvious effect, the irreversibility of time, is not an obvious consequence of the fundamental laws. The effect is rather far from the basic laws. It takes a lot of analysis to understand why. And the effect is of first importance, my memory, my characteristics, the difference between past and future, are completely involved in this. Yet understanding it is not immediately available just by knowing the laws. The laws of physics do not have direct, obvious relevance to experience. There are often great distances between the detailed laws and the main aspects of real phenomena. Like a glacier, you watch it move, rocks falling, ice flowing. You don't need to know it's made of hexagonal ice crystals. Yet the character of those crystals, if understood well enough, is the reason for the glacier's motion. But it takes time to connect them. In fact, nobody knows enough about ice crystals yet to fully understand glacier behavior. Although we've been talking about fundamental physical laws, I must say immediately, knowing all the fundamental laws as we know them today does not immediately give you understanding of much. It takes time, and even then it's only partial. Nature seems designed so the most important things in the real world are complicated accidental results of many laws working together. So let me bring this all together. Why can't we reverse time? Why don't broken cups reassemble? Why doesn't mixed ink separate? Not because the laws of physics forbid it. Every collision, every interaction, every force works perfectly in reverse. The reason is statistics, probability. The overwhelming number of ways things can be disordered compared to the tiny number of ways they can be ordered. A cup has one way to be whole, millions of ways to be broken. When it breaks, it moves from one ordered state to one of millions of disordered states. That's likely. But for it to go back, for millions of atoms to accidentally coordinate perfectly to reassemble,